Can you see my screen?
Yes, sir, it's visible.
Okay, thank you. Okay, so we looked at some of the lower layer issues, and specifically we looked at how to make two machines communicate directly over a link and how can we make more than one machines sharing a link. The link is still the one link out there, either shared or dedicated. So next things that we are going to go slowly to the actual higher layer networks, local area networks in the higher layers. As I said, a wide area network where there are multiple links, nodes are indirectly connected and so on. But before we do that, we talk about something that is at the heart of that design basically. So protocol architecture and layering. So today's class will not do anything greatly technical, but it's more a way we design the software network stack, software hardware network stack, and the layers that everybody talks about. So we'll see what. So you think about modern day networks, there are a huge number of services running on there. Everything is network enabled. And every day you want to have new things that are network enabled, new devices, okay, new software services, everything depends on networks. And there's a huge bunch of protocols. And I'm just listing some common ones that you have heard about without kind of classifying them for what they do or anything. So you hear basically Ethernet protocol, TCP, UDP, IP, ARP, RARMP, etc., 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 etc. Okay, and that list is like endless. there are too many of them. I've only listed a few. So these are protocols which are kind of again rules for communication sort of, and then there are myriad of devices also. Okay. So Ethernet per se is not just rules for communication. When we do Ethernet, we'll see it is also, both combination of lower layer physical, electrical signaling and so on, and rules for communication like what should be frame structures and so on. But other ones are primarily rules for what are the language that two endpoints talk. And myriad of devices. Okay. Not counting end devices like your laptop, desktop, who are the actual end users of the thing. But if I look at the network infrastructure that provides those services, you have so many terms. You have seen access points, L2 switches, L3 switches, L2, L3 switches. There are L4 switches, routers, load balancers, firewalls, UTM. Again, there's a huge bunch of things. Some of them are pure hardware based, like an L2 switch will be, but nothing is pure hardware. There is a firmware software loaded. Okay. But what we mean by hardware based, so these are interesting digressions. So you buy a box. Okay. Just one second, please. So when I say hardware based, I say basically you buy a box, but the box will have some dedicated firmware software also loaded in it basically. Okay, so it's not that it's pure hardware, and some of them are software based. Okay, so you can actually buy some of these things like load balancers and all. You can buy a box which you will physically put in a rack and connect with wires and so on, or you can buy basically a virtualized appliance. Basically, they will give you a bundled virtual machine that you can run on any server. They will specify some minimum system requirement and so on. So you get the same services, the load balancers as a software. Okay, and there are software load balancers. Load balancer is one example, but firewalls, etc. Many things actually, either you can buy boxes or you can buy, but not all of them. For example, access points you cannot buy virtualized things. L2 switches no. So lower layer, smaller things, no. Higher layer, more costly things. Many of them you can get in both versions nowadays. Okay, but the point is there's a huge variation. And the other thing, before you go to the big questions, is remember, unlike the small things that you see around you, the network is not controlled by one single entity. IIT Kharagpur controls IIT Kharagpur's network. So if I want to upgrade something, some software, I can do it. I want to replace some devices, I can do it. But then a network is something that connects everybody. So IIT Kharagpur cannot tell IIT Bombay that, see, I'm upgrading this thing, you should also upgrade there. That's article bomb-based decision, whether they want to or not. Okay. So we say that they are not under the same administrative domain. Administrative. Okay. So no single administrative domain. So not only there is a huge variation of protocols, devices, services that all depend on the network. We're kind of crippled without a network nowadays, but there is no single entity that will control everything basically. Okay. So how do I manage all this? So big questions. Can we organize all this to understand them better? How do you even try to make sense out of it? Okay. Do you study all of them together? Okay. And this is like giving if I give you 1 million lines of code to study, do you start like reading files arbitrarily? Or do you try to group things into saying, okay, this does this, let me understand this module first and so on. That's how you do things, right? Excuse me. Now, fine. So what is there? How do I organize it? If I want to write something, do I have to implement it from scratch, right down to sending the bits out? You have already seen that we don't do that. Okay. In your network lab. And then I have got a network stack. Okay, you are using a TCP/IP stack, Ethernet, etc., etc., etc. If I come up with a better implementation of some existing protocol service, does everything using it or whatever the old version was using all have to change? How do I integrate it with everything that exists? Now, if you see for a second, because there's a lot of software involved also, it has something analogous with software design also. As I said, like if I give you like hundreds of thousands of code, you don't try to understand it together. Okay, you try to organize it somehow. Okay, you want to plug in a new function. Okay, you should not have to do everything. There should be libraries, etc., already helping you. Okay, you want to change a function. Okay, there are ways of changing the implementation of the function without affecting anybody who is using that function. Okay. And as I said, while I may have administrative control over some parts, okay, I do not ask others to change just because I change something. So how do I do this? Now, nothing is perfect. Everything cannot be done. You cannot say, I want to do this great thing and everything will work perfectly. But how do I make this entire big thing spread over lots of admin domains all over the world, different people controlling it? Okay. How do I make sense out of it? How do I make things work? How do I change things and make the changes seamless? How do I add new services to it? What is the design philosophy that kind of guides it? Okay. So those are the questions that we'll try to kind of see what people have done to tackle them. So obviously that no ad hoc approach will work. If I try doing things my way, you try doing things your way, sitting in your own offices. Okay, first of all, a protocol will not exist. A protocol is an agreement. Your third assignment onwards in your network lab will stress on that. Okay, it's an agreement between the client will say, I will send you first. I will send you exactly this. So the server knows what to expect. So both what message gets exchanged, what is the format of the messages, all those things have to be decided a priori. And the other thing is basically in a networked world, almost nobody writes, not I would not say almost nobody. There are softwares for which both the server and clients are given by the same company. But for many things, the server and the client will be written by two different entities. You have the standard web server softwares. Okay, you design your web servers using any of them, IIS engines, whatever, basically. Okay, but then it should work with Firefox, Chrome, Edge, whatever. I should be able to write my own browser. And again, this is an online semester, so I don't think, given everything, we don't want to stress you too much. But in the labs, we used to do this kind of very basic HTTP server, client server. And then your client will actually connect to an existing running web server somewhere else and actually get some text data out of it. So, to understand the meaning of protocols, basically. Okay. But we'll give you a view of that still. Okay. So nothing ad hoc will work. People have to get together somehow have to follow certain rules and so on. So the two important keywords, okay, as was there in the title. One is protocols. People have to agree on some common standards. And if you deviate, you're out of my network world. You cannot use my services. If I say that I want to have a client which will work this way, not the standard HTTP way that everybody agrees on, fine, you can make your client work with your own server, but the client cannot connect to any other server. So nobody else will use it. And sometimes that is fine. Sometimes you are designing some, software only for your internal use and you want to optimize it. But in this course, that's not our goal. We talk about the internet as a whole, the entire network. So there has to be some common standards. But then who makes everyone agree? What are those processes? How do you get the community to accept a new protocol? How did people decide that TCP should be this, IP should be this should be the headers of IP, this should be the format? This is what IP will do. How do you decide on HTTP, SMTP, all those mail protocol, everything that you are running now, FTP, Telnet, all of them have some specific format, specific rules for who will send what first, who will be the next one, what is the response, what will be the response codes, what will be the format of the messages, who decides that? Okay, so for everything, there's a lot of organizations involved. We'll talk a little bit about some of them later on. For internet, for example, there is this organization called IETF. It's called Internet Engineering Task Force. Okay, so these two terms, this RFC is the other term. Anybody knows what an RFC is? Yes, no? You must have heard the term RFC.
No, sir.
No? Okay. So RFC stand for, again, you're not supposed to know. It's not that you have come across in any course on this. It's called Request for Comments. Okay. And the definitive document for a protocol, okay, is not a textbook. It's not somebody great who wrote it. It's the RFC. You must conform to the RFC. Does that mean for everyday use you have to read the RFC? No. For example, in this network course, we'll point out RFCs, but you probably will. I would request you to go take a look at them to see what they look like. Okay, these are documents that people write, but this is the one that defines exactly the structure of the protocol. What happens, what are the messages, what is the format, who sends what are the operations supported, everything. So typically on the internet, if you want to propose a new protocol, you'll have to propose it to IETF. And if IETF thinks there is value in it, it will go out as an RFC. So RFC is RFC. RFC has request for comments. So then they give people 3 months, 6 months time to take a look at it. People implement it, some people, and then there'll be comments and everything. Based on that, if it is still found to be valuable, then it becomes what is called an IETF standard, internet standard. Okay, but there are many protocols which has not, the RFC has become the definitive document rather than gone to the internet standard stage, basically. So there are lots of internet standards, but you will, for any protocol, when people refer to it, what is the document behind it, people will say RFC 2310, RFC 728, RFC. So every RFC has a number, basically. Okay. And there are RFCs for writing RFCs. That's very interesting. How do you write an RFC? There is an April Fool's Day RFC. Okay, so it's very interesting history out there. Okay, but point is, first thing is that people agreed long ago that there has to be somebody guiding in. IETF came out of, as I said at the first class, a little bit, very little. The internet came out of originally out of this ARPANET and all from the Department of Defense in the US. And then slowly that evolved, and then ARPANET community kind of handed over to commercial establishment. But then people realized that you have to work together or the network will not grow. Okay, no single organization can dictate it basically because it has to go worldwide. So IETF is the organization that evolved. There's a history behind it. And that's the one that controls which protocols. For everything, there is an RFC. For IP protocol, there is an RFC. For TCP/IP, there is an RFC. For UDP, there is an RFC. For SMTP, there is an RFC. Sometimes more than one RFC. Because you do something, then you modify something later on. So you'll have an RFC that adds to the previous RFC, an RFC that obsoletes the previous RFC. You'll start with the thing, this RFC obsoletes RFC 721. Okay. So you go through that process, and the RFCs are the definitive documents. So when you implement a protocol, okay, not for this class, but beyond this class, if you implement a protocol, you do not implement it reading the textbook. You implement it from the RFC. So that is the definitive one that defines the protocol. Okay. When we do, maybe in 3-4 hours from now on, we start with IP and so on. I'll point out some RFCs for IP. You can go take a look. Not requirement for this course, but you should take a look at RFCs and so on if you're in the networks. Okay. Similarly, there are organizations. I'll talk about it when I come to IP. These IP addresses. I have to make the IP addresses unique across the world. How do I make IP addresses unique? If I just choose something, okay, and somebody else chooses something somewhere else, that cannot be necessarily unique. So there are organizations like IANA, and so on, NICs and so on. I'll talk about them later on. Like actually, there's lots of NICs, which actually controls how are the IP addresses distributed across the world. So you cannot just go and start doing your own IP. You can, but there is something called a private IP, public IP we'll discuss. But the thing that goes out publicly on the internet, it's not that you can just say that, oh, I want to use 232.5.7.23. Okay. You're not allowed to do that. Now, what does it mean you are not allowed to do that? You can do that. Nobody can stop you from assigning a static IP like that. But then bad things will happen to you. You may not be able to route and so on and so forth. IP conflicts may happen. So you want things to work for you as well as for others. You have to play by the rules of the game. So there are different organizations which sets these rules for protocols and so on. So protocols is IETF for the internet set of protocols. Okay. Similarly, there are IP address assignment, there are organizations. There are many other organizations. Okay. And secondly, now that you have these protocols, how do you organize these protocols? You organize them in layers. So layering is kind of the fundamental in designing the entire software, or I would not use the word software again and again, building the network stack. Okay. So you organize the protocols into layers for the network stack. So what we will do today is to focus on the layering part. Protocol, the definition is understood. I introduced IETF and RFCs. If you are interested, you can go take a more look. And RFCs, as I said, I'll keep on pointing out as we go. Do the actual internet protocols a little bit here and there. And I will talk about at least 1-2 other organizations. Okay. So what we do when we design these protocols, okay, what people have done, it's been, I don't say this has been here for quite some time, but you follow this same philosophy. The entire task of communication was broken up into modules and layers. And each layer expects, so it's kind of a hierarchy thing. And each layer will expect something from the service from the layer below it and provide some service to its higher layer. And strictly speaking, when I expect a service from a lower layer, I do not care about how the lower layer is providing me the service. Okay, which means the lower layer can change itself as much as it wants, as long as it guarantees me the same service in the same format. It's somewhat akin to changing libraries, changing functions without changing their prototypes. It is exactly kind of what it is. So you can think about that the lower layer gives you, sort of. It doesn't work exactly like that. I'll talk about it as we go on doing the protocols more and more. But broadly, the lower layer kind of gives you a set of functions that the higher layer can call. Okay. You have already seen this in your network lab. Okay. So your transport layer is giving you the sockets. Now you have to know a little bit about transport layer, but as long as that interface is fine, you know, if you drop something in a TCP socket, which is just a name to you right now, you know it's going to pop up on the other side. You know, if it's a UDP socket, the message is going to pop up, but may or may not. So it gives you an interface. It gives you certain guarantees on that interface. OK. Now it's up to you. But then now theoretically, I can change the implementation of TCP layer completely as long as I keep that socket interface the same. You don't have to change a single line of your application code that you are writing. And not just at a TCP, we'll look at the layers. The same thing happens at the lower layers as we go. Okay. The topmost layer is application, which is the one that uses the network infrastructure. So all your standard protocols like HTTP, SMTP, your mail, web browsing, telnet, FTP, SSH, everything is at the transport layer. Anything that you can think of, okay, that you use finally. So these are the protocols implementing the different services that we all need. Some common functionalities from the network, okay. And the common functionality that it needs from the network is like this, as I said, like, you know, from your socket experience, that I need some reliable transport between the two endpoints. That's the functionality I'm saying. How the network is giving me that functionality is not important to me. I got a socket interface. I know if I make the socket call, I do this, and do this, this will go. Okay. And there have been two types of or two approaches to layerings. They're kind of more or less similar, but just a little bit different the term. So original was OSI layer. So, and now the TCP/IP layer is the de facto standard for modern day internet. So internet uses TCP/IP layers. OSI layers were standardized again by a couple of organizations. ISO, called International Standards Organization from US, and CCITT, it's actually a telecommunication standard. It has a lot of telecommunication standards in general, basically. It's a French organization, is kind of the European part of the thing, basically. So CCITT standards are very famous in many things like telephony and other things also. And you know, early days, as I said in the first class a little bit, there's a lots of different types of network. Big companies, IBM had their own SNA network, DEC has DECnet, there are other networks evolving. Okay. And so the need came kind of to say that if I want to interoperate between these networks, how should I be doing things? So OSI was an approach towards that, but as internet gained speed, TCP/IP became the de facto standard, simpler layer, basically. So OSI layers, there are 7-layer model. Okay, as long as you are in school and maybe a little bit after that, you should remember these 7 layers. Okay, people will ask you, tell me the 7 layers of OSI. Okay. So application, presentation, session, transport, network, data link, physical. So this is basically your where. Okay, there's a lowest thing, and then this is on the top, basically. Okay. And then TCP/IP, why I do this is just basically, it basically clubs all these 3 things together in application. Actually, this part a little bit here and these 2 here in application, a little bit of session also. So we'll study this. Okay, and then at the end, I'll point a little bit out as to how OSI differs out here. Basically. Okay. So what is the physical layer? Is the physical interface between data transmission device, that is a computer, net, whatever, and the transmission medium or network. Okay. So it specifies basically raw transmission details. We have studied them already, many of them. What would be the connector type? How many pins will you add? What will be the wire connections? Medium type. Okay. Voltage levels, encodings used, and so on. When I do Ethernet next, okay, I'll say that, you know, when we say 10 base T, 100 base FX, okay, we'll see it specifies the type of medium, accordingly the type of connectors, okay, and so on. So all those things that we talked about, encodings used, voltage levels, etc., all those things are there. Okay, the important thing is at the physical layer, there is no notion of frame, packet, nothing. It just sees at a raw bit stream. Okay, whatever you give it, it sends. So if you give it 1000 bits in a go, it will transmit 1000 bits. Okay, So the notion of framing that I did is actually slightly higher than that. It won't be there at the physical layer. Physical layer just gets the bits, encodes, knows that okay, this is the encoding, that's the voltage level to be used, okay, everything, and just connect. And it's mostly, as you can see, implemented in hardware. We will not do the electrical details at all. Okay, connector media will look a little bit from practical point of view. At the end of the course, I hope I have time to kind of, I will have time to kind of put, not necessarily end of the course, but after we go some way down the course. So that's the physical layer. Data link layer is exactly what we have done so far. It ensures reliable communication between directly connected nodes. Now that link can be shared, okay, can be dedicated to two nodes, more than one node. So all those details about CSMA, this, that, etc., that you have come in, comes into data link layer. Okay. Now what is the interface then? If this is my data link layer border, then the higher layers can send drop this thing knowing that this will be transmitted here. So it doesn't have to worry about what voltage levels and so on. So when I'm designing a software out here, okay, I just think about what is the data link layer going to take, and the data link layer packet is, or the kind of the unit of thing is the frame. Okay, so it deals with framing, deframing, all those, making those frames and so on. Okay, flow control, error control, all those things that we have studied about. So that's why it's called data link layer. Okay, it's one link basically. So the higher layers don't have to worry about all those lower layer details about how to handle, how to encode, how to do this, how to frame, what is my frame size, nothing. But you have to worry about its own things. Okay. We've done so far. Ethernet is one of the most well-known protocols in this layer, and this is associated 802 IEEE protocol out there. We'll talk about that. Okay. Now, Ethernet actually is a bundle of things. It's not just data link layer. It also includes physical layer. There are many different physical layer interfaces. We will talk more about this. But see, this is where I come back to what I was telling you sometimes back, that things get a bit confusing as we go on. Okay? So you look at any textbook, it'll tell you that, you know, that functionalities, if you run this is a standard question that people will ask you, oh, fine, 5 layers, tell me the functionalities and so on. You know, Grand Vivas, exams, this, that. Okay. So people will say framing, deframing, flow control, error control, these are the standard functionalities. Then I ask you, what is the most, the most famous data link layer protocol that you do? And you proudly say Ethernet. But Ethernet does neither flow control nor error control. So things get little bit confusing, but then you have to try to make sense out of it. When we do Ethernet, somebody asked me, why don't we do it? Okay, because it's a data link layer protocol. You ask yourself question. It's a data link layer protocol. Okay, it is said that data link layer should do framing, error control, flow control. Ethernet is a data link layer protocol. Why does not do it flow control, error control? Okay. I will not answer this now. All I'm trying to point out, you should ask basically. You should see this confusion, this ambiguities and so on, and say, why did they make that design choice? People were not stupid. Okay. So why do, knowing everything, why did not they put in flow control, error control there? But Ethernet does error detection and all. Let's say the CRC check is there in Ethernet and so on. Okay, so that's data link layer. Then I go to network switch layer, which is what we'll start next after this class, okay, when I come back. So network layer now says, fine, so I know how to communicate with, I have this lower layer thing on which I can call some functions to send my packets on the way, okay, to the other side. But then how do I reach the other side? Because now I don't have only single link connecting them. Everybody in the world is not connected directly with everybody. There are lots of intermediate routers and so on and so forth, machines through it goes through. So the primary function of network layer is to route, to send the packets from a source to a destination when they are not directly connected. They may be directly connected, in which case my job is simpler, as simple as that. But in general, they will not be directly connected. So how do I find a path? How do I find a path, first of all? And just think about it again, nobody is going to tell you a priori basically. The internet is vast. Links keep on going down and up. Again, later on after we finish IPTCP, I'll point you out to some sites where you can see the measurements on the actual internet, the status of the internet every day and so on. Okay. Not everything, but nice sites to follow. Okay. So in the presence of that, so I have a route to some machines in Los Angeles, but then some link, the route is just a path in a graph basically. So some link went down. How do I know about this? How do I find an alternate path? Okay. How do I efficiently manage this path after I find out? Okay. And strictly speaking, I'll come back to this when I do IP addressing. When I talk about a machine here, it means a network card more specifically. So you can actually have more than one network card doing this functionalities and so on. Okay, but again, this is less important right now. We'll come back to this in the IP. So the primary function is routing. Okay, it does not care about reliability and all these things. Packets may not reach order. So in data link layer, the data unit, the protocol data unit that we talked about is called frames. In the network layer, it's called packets. It's the standard terminology. They may not reach in order, get lost, etc. Those are not so there is no error control, no flow control. Those are not the functionalities of network layer. It may have some other functionalities like we'll see for IP called fragmentation and so on, but the primary functionality is routing. Okay. Implemented usually in software. IP is the most well-known protocol that is there, and these are the issues we have not studied so far. We have studied up to the data link layer sort of. Transport layer. Now your packet, I know how to route your packets from one machine to another machine. Okay. But then in one machine, there are lots of software running, lots of applications running that are relying on the same network. So how do I decide which packet is for which application? This is a question I posed to you on Network Lab. I have 5 different browser windows open and none of their packets get mixed up. But they're all coming over the same wire going out of the thing, over the one network card that your machine has. Okay, so they're all coming together. So transport layer deals to now not just machine to machine, but end to end. Okay, so we say whatever you call it, process to process or application to application delivery. Okay, and this is what I said. So network layer only gets the packets to your PC laptop. How does the right things go to the right browser, the right application? You have a telnet running, an FTP running, SSH shell open. Okay, you have a browser running. All of them are coming to the same network card, the same network stack in your OS, but none of their packets get mixed up. Okay, so basically the primary function of transport layer is multiplexing, demultiplexing different applications data over the same network connection. Okay. It can give additional guarantees like TCP gives reliability in order, but that's not the primary function. And implemented usually in software. And TCP, UDP are the most well-known protocols in this layer. We will study both of them. Finally, you have the application layer. This is the application-specific services. There's too many of them. Okay. And here is what, so the OSI layer actually broke it up into application, presentation, and session. So session does some of the works of the transport layer. Okay. So this, remember in the transport layer, we already talked about connections. Okay. We'll see later on what they mean exactly. So now you can maintain sessions and all. So little bit, I will not go into what sessions are exactly. They have different meanings. So, but partly here, you do the session management here. Application is application. But then some of the other things like doing encryption, doing compression, and so on, you kind of put in the presentation here. So you can think that an application, if it requires a compression, will ask for the service of this. Okay. So just think that this presentation layer, just think that there are 3 functions: compress, encrypt, do nothing. Okay. You want to compress, you put this here, and then it compresses and then sends down. You want to encrypt, put this here, encrypts and go down. You don't want encryption, don't want compression, do this, it goes down. So this is just, this is just metaphor basically. It's, you're going to have much more. But kind of services that the presentation layer, it deals with the presentation of data to the lower network, the higher network. So when it goes to the other side, the presentation layer will decompress things, decrypt things, and so on if necessary. You could have done both. Okay. So all those services. TCP/IP is a simpler protocol which kind of clubs says that all those is application business. You want to compress, call some compression software before you pass the data to the TCP layer. And the session version, everything is TCP's business. So TCP is mentioning like end-to-end delivery. So it's a somewhat simpler layering, which is why it has become more popular. But the lower layers, there is almost no difference. And here, basically, the terminology for oops, sorry, not here. Application, there is no this thing. It's a segment or message. Okay. This is what is the generic term is protocol data unit. Okay. So protocol data unit is the final thing, okay, that is generated out of that layer. Okay. So if I look at the layerings, some layers, okay, here. So this is my sender, this is my receiver. So if I look at the layer here and the same layer here, so there is a PDU of this layer, which, as I said, in the data link layer, you name it, call it frame normally, in IP you call it packet, in TCP layer you call it segment, okay. And this sends the PDU, it sends thinking that it is sending to this. Now it actually goes through here, and we present it from here to here. But to this layer, okay, it seems like it's communicating with this. It does not know how its packets are getting, or packets, messages, whatever getting transmitted out there. When you're sending through that TCP layer, you say that this is what, this is what the unit I'm getting, this is the unit that the other side is receiving. Okay. And we'll see this will become more apparent later on as we go from the higher layers. Okay. There's a chance that it may be broken up into smaller data units. You have already seen this. The application layer, you are designing FTP. Okay. We want to send a file, but the entire file cannot be sent. So you break it up into lower things. Okay. Not just the breaking up that you have done, but again, underneath when we do TCP, we'll see. Okay. So you may need to break it up into smaller data, and each layer will add its own control information. So this is what is called the header. So PDU at any one layer is the control info added by the layer plus the data unit coming from top or bottom. Top actually, sorry. Okay. And this PDU, as I said, is a generic term. Is called differently at different layers. Called frame in data link layer, packet in network layer, segment in transport layer, message or data in application layer, and so on. Sometimes we use also segment, message also in transport layer, but segment is a more common term basically. Are you with me so far? Yes, no? Someone respond, please. Can you hear me? Oh God. Can you guys hear me? Yes. Okay. So this is what your packet, the data will look like. So this is the user data. And this is what is called encapsulation. Why do we need to put the headers? We'll see. Okay. Why do we? We have seen in the data link layer already some control information. The frame check sequence, for example. Okay. So you will get the top layer. This is what you're passing in your socket. TCP will take your data completely, add the TCP header to it. We'll come to IP. IP will take this entire thing as the data. It does not try to do anything with the TCP header. Okay. Then we'll add its own header. Then data link layer will take this entire data, add its own header, and then physical layer will, there is no header, it just goes out. And then the other end will see this. At the data link layer, you will look at this header, decide what to do. For example, there may be more than one protocol using the services of this. So we'll see one of the fields out here tells it which protocol software to give it to. Should I give it to IP? Should I give it to ARP? Okay. But then beyond this, there is no need for this header. So this will now take this header off, strip the header off, give the data. Now this layer knows what is the format of this. So it knows this is the IP header. Okay. So we'll look at this, take appropriate decisions. We'll see what the contents of this, strip the header off, go up there. So as you go down, you keep on adding header, 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 header. On the receiver, as you go up, you keep on deleting header, header, header. Finally, the user gets, as you have seen in socket, only the user data. You don't see the TCP header, IP header that is being put on your packet. Okay. So how many layers? Well, it's pre-decided for you already. Okay, right now there's, nobody thinks of changing the TCP IP layer, but this simple thing, each layer will take data, possibly break into smaller chunk, add its own header. So more the number of layers, more headers are added. More headers you are adding, remember headers are pure overhead. You want to transmit the data. So your percentage of overhead increases, per data item increases. So you don't want too many layers, but you don't want too few layers because it defeats the purpose of layering itself. You want to isolate the functionalities in layers. Okay. But why do we need the layers at all? Because apparently now it seems that I am just putting them. That we'll do when we study the protocols. We'll see every protocol for working will require. It's a standard example that you will understand now also. If I want to send somewhere, my machine, I'm sending a mail to something, I'm doing a web browsing to google.com. Somewhere I have to put that IP address of google.com in my packet so that the entire network as it goes through knows that this packet is for that destination IP. Where do I put it? I put it in the IP header. Okay, and it will be carried with the packet. And the IP layer at each router will look at it and say, oh, this is for this is not me, let me route it. Okay. So this is what kind of your broad physical architecture will look like. And this kind of tells you, this picture is not perfect. I borrowed it from somewhere. It's very common. Okay. So you will have all these things, anything connected to your PC, laptop, scanners, phones, okay, network printers, etc., etc., etc. Then you will have wireless access points, or you will have edge switches. These are the things that sit in your hostels. On your wings, you will find the edge switches. It may not be on every wing, okay, but on every floor, mostly for large hostels, have at least one switch box, basically. Okay. Then they will come into bigger level switches, which are called distribution or aggregation switches. Two names for it. Okay. Then they will come to even bigger switches. So distribution switches are again mostly in hostels, departments. Okay. But for very small cases, sometimes in CIC also. Core switch is what will sit in the CIC. It does sit in the CIC. And then many things will come from the core switch. Normal data traffic. I can connect a storage which requires network. Okay. IIT Kharagpur's many telephones, not all, actually go through a telephony server. Okay, which basically takes the telephone lines and converts them into data and sends it to the thing. You have the wireless controller that manages your access points. You can put servers connected to the network. It doesn't have to be. This is just a representative figure. Okay, it's not that the servers will have to connect to core switch. I can have smaller level aggregation switches here and then connecting to here also. Okay, then you will have a UTM firewall router. Again, these functionalities will be kind of, we will see. I'll discuss a little bit there, and then goes to the internet. Okay, and this is what you will see in most textbooks. You will see that this is kind of a cloud. And we'll try to demystify parts of this diagram as we go on. Okay. So that's about it. But just to give you an example. So you see, Why do we do this layering? See, data link, take this thing. You heard about that on your network card. Okay, you buy any network card. Okay, and it works with your Linux, Windows, all OS. Okay, so what do you get? You get basically network card plus a driver. Okay, so one second. Thanks for example. Yeah. So you see, if you have this one, sorry. If you think about your, give me a second. So this network card plus driver, which is software, okay, is basically your data link layer plus physical layer. Okay, and then it gives you, okay, a standard interface. So there are standard interfaces designed for Linux and Windows, which says Linux says that if you want to work with me, you want to work with a network card that is compatible with Linux, this is the set of function calls that you must give me. I'm not going deeper into that, but that's the idea. Okay. So then network card hardwares will differ. Windows similarly says that. And these two interfaces are different. So the network card hardware is the same network card works both places. But then the driver software kind of maps this functionality to the functionality that is required by this, the common functionality that Linux requires or the Windows requires. This is why your drivers are different. Okay. But now the advantage is because I have said that IP will expect the lower layer to work like this, I can actually change my network card and not affect anything in the IP layer or anything above. So I can completely change my network card. I load the driver, the interface remains the same. So the notion of interfacing is extremely defining a clean, proper interface is very, very important. So the higher layers kind of see a function abstraction. Okay. So that's at the lower layer. You have seen an example at the socket layer also. I can change my applications anything, or I can change the TCP implementation completely without having to change my applications at all. But as we do on, as I said, network is kind of confusing at places. We'll see this abstraction breaks down some places, because to do this abstraction exactly, okay, we'll see that sometimes performance suffers. And there are other related things. See, TCP, like network cards, different people will manufacture. Applications, different people will write. But when we talk about a TCP IP software, okay, you don't see an IP implementation without TCP or a TCP implementation without IP. So TCP IP kind of comes together. And there's another bunch of protocols. We'll see. So people optimize a bit so that I lose the layering a lot, because I do not need that functionality, the difference by having to change one without having to change other that much. Okay. And I'll point out at some places that the abstraction is lost a little bit because of performance. But then again, I'm doing it at the TCP IP and so on, where I don't need to separate, because usually it will come bundled as a software. I don't have to change IP. It's almost never that I change IP without changing that software basically. But as I said, down below it makes even there it's a cleaner interface, so they understand the code much better. You can modify, manage your code much better. So that's all I have to say today. This is the last of the extra classes, so no more extra classes, no class next week. I will see you back again on Monday, the week after, and we'll start with local area networks, and then go to IP, TCP, and so on. Local area networks, it's data link layer. Most of the issues underneath things we have already covered. So I'll just point out basically what it is, some practical things, existing Ethernet issues, and so on. And then IP, TCP, etc. we'll have to study from scratch. Okay, so I'm done. If you have any questions, you can ask me. Otherwise, the class is. Yeah, go ahead, please.
Excuse me, sir. Sir, I actually wanted to talk something about the networks lab.
Okay, So then one second. So class is dismissed. If you want to leave, you can leave. Otherwise, you can stay. Okay. But if you want to leave, you can go ahead. Okay, go ahead, please.
Yes, sir, I was doing the assignment and I'm facing some problems. I know but I would like to have a little more of time. So is there any possibility of getting an extension? Like I talked to a few of my friends as well. They were also asking for it.
No, this is kind of simple thing at the beginning. Okay. See, we have bigger assignments to come. We'll think about extensions there and so on. Okay. This one you submit. This will be low marks assignment. So whatever you can do, you submit. What is the kind of problems you're having?
Like I wasn't able to get the IP address properly. I think there's some problem with my code itself.
What do you mean by get the IP address properly?
I didn't get it. Can you please repeat?
No. I mean, what do you mean by get the IP address properly?
No, the.
Oh, the get host by name.
Yeah.
Yeah. Okay. See, get host by name, I did not do in class because there you will get so many code snippets and all also. We have told you that you cannot copy code. Okay, we should not copy code. But then to understand, it's just understanding the structure, which is mostly structure. So spend some time. I think you will be able to do it. Okay. And there are partial marks and so on. So we have a plan. Okay, and these are these have always been 1 week assignments. Time immortal. So I think you will be able to do it. Otherwise, fine, submit partially and then we'll see. These are anyway going to be first assignments, so not too much marks and so.
Got it. Like you only mentioned in the lab, like if it is getting a little loaded, we can ask.
Yes, I know.
Yeah.
Thank you for telling me this. No, I appreciate that, but for everything that is loaded, I'm not going to change that deadline. For some assignments, we know what is going to come. Things are going to get a little bit more difficult. Okay. So there we will consider. The other thing that I'm telling you, Satvik, and everybody else also, that you are in the 6th semester for the first time, obviously. We have taken many 6 semesters. 6th semester has always been, the last probably 10-15 years at least I can remember, has been very tight. You have to plan your time very well. Okay, because it has 3 systems lab, and the problem is that until you do architecture, you cannot do OS. Okay, networks actually was long ago in the 7th semester. But then the problem was people complained that, if you fail in network, then you have to sit for supply. If you fail in network lab, there is no supply for lab also. Okay. So we had to move, we exchange theory of computation and this. Ideally, I would prefer to teach networks after OS. So we can do a lot more in lab and other things. And then database was there because people wanted to do database before they went for placements and so on. Okay. So there are 3 systems courses, assignments in every one of them. Please keep me posted. This is not to discourage you. Please keep me posted on the load and so on. But lots of time we have found out also. Please also discuss among yourselves that start assignments in time, plan things a little bit. Okay. Some assignments later on when we come, we understand it's online semester, we may extend. But not at the beginning, because again, this is, I have always found that if we tell you at the beginning that this is 2-week assignment, for the first week, nobody does anything. And in offline class, I can force you to. I can ask you to come to lab and show me what you have done so far and put a small amount of marks in it and so on. In 3 hours, we can do that. Online, it's difficult, basically. It doesn't make sense also. So start in time, keep on doing it. This one, I think, the get host by name, there's still enough time. This is only Friday. You'll be able to do things. 1-2 days extension, we'll see. If necessary, we'll do that. But the next assignment will start.
So just to confirm, we can expect an extension in the.
No. Do not expect an extension. Okay. We'll see that on Monday. See, Satvik, if I extend now, this is going to just pile up on your pressure because I cannot extend the next assignment, giving the next assignment because I have a Monday class.
Got it. Yeah.
It's just going to pile up, basically. So just try finishing it. This one, I think you try finishing it. And Monday I'm not there also to make decisions. Monday I'll be extremely, I will not be able to give any time at all. So this one just finished. For the next assignment, you will get 2 weeks. You will work in groups. So as long both of you work and you plan things properly, you should not be in trouble. And then we'll see some small extensions. So actually, when I come back at the beginning of the semester, we don't do it. But when I come back, I'll be talking with the OS teachers also. So we know what they are doing and so on. So we'll try to do something so that not too much load comes on the first 2 days of the week or something. We'll see. Okay, any other questions? Okay, if not, no class next week again. So I'll see you the week after. Thank you.